We are moving past the era of humans typing prompts into language models. We are building systems where agents orchestrate other agents, a framework we can call Software 3.5. But dropping a raw frontier language model directly into a production environment to handle these tasks autonomously results in systemic execution failure. These failures stem from three distinct architectural bottlenecks. First, inference latency. Second, context fracturing. And third, execution collapse. As the models themselves become a commodity, the true enterprise value of a product depends entirely on the infrastructure stack engineered around it. There is a pervasive assumption in the industry that simply scaling parameter counts will naturally fix all of these reliability issues, that a sufficiently intelligent model won't need complex orchestration. But software intelligence cannot override physical hardware limits. Without the right environment, the system jerks and freezes, unable to execute basic sequential logic. This is why 95% of enterprise AI pilots currently yield zero measurable P&L impact. The models are highly capable, but the surrounding architecture is failing them. Treating a language model as a standalone product guarantees a failed deployment. It must be treated as a component, requiring a highly specialized processing environment to function. The first structural barrier to an autonomous system is latency debt. When multiple agents must communicate in a continuous feedback loop, even minor delays break the system entirely. To understand why this happens, we have to look at the two stages of processing a prompt. The first is prefill, ingesting the input tokens. This step is compute-bound and highly parallelized, meaning the hardware handles it efficiently. The second step is decode, generating the actual output tokens. This process is strictly sequential and memory-bound. This schematic shows traditional GPU architecture. During decode, weights and cache data are shuttled back and forth between off-chip memory and the compute core. This physical transit creates a massive bottleneck. Generating hundreds of reasoning tokens forces constant memory retrieval, choking the pipeline. The physical distance between the memory and the compute core dictates a hard limit on how fast an agent can iterate. This renders standard inference hardware untenable for real-time autonomous systems. To bypass the memory wall, hardware engineers are implementing disaggregated inference. Instead of running the entire pipeline on one chip, the workload is split. The compute-heavy prefill stage runs on compute-optimized chips, and the sequential decode stage runs on memory-optimized hardware. An alternative physical solution uses distributed on-chip SRAM. By keeping the memory directly on the chip, the system bypasses the off-chip shuttle time entirely. But silicon is only half the solution. In software, we apply speculative decoding. This technique involves deploying small, highly specialized subagents to rapidly generate probabilistic guesses for the next token sequences. The massive frontier model then steps in to verify those guesses in parallel, rather than calculating each individual token from scratch. By separating compute optimization from memory optimization, both in the silicon and in the software, we finally achieve the raw inference speed required for an agent to reason in real time. Once the system is fast enough to think, it needs accurate memory to act. This exposes the severe limitations of naive retrieval augmented generation for autonomous decision-making. Standard vector databases rely on single-dimensional textual similarity. As seen in this 3D vector space, they can capture the semantic meaning of three isolated facts, a user's employer, a government sanctions list, and a credit request, but they completely ignore the causal architecture between them. Because there is no structural connection linking the applicant's employer to the sanctions list, the model is forced to guess. Without explicit logic, the agent will often simply rubber stamp a fraudulent approval. To solve this blind spot, the system requires context graphs, or knowledge graphs, acting as a structural memory layer that maps entities mathematically. Instead of floating chunks, data becomes nodes, and explicit relationships become queryable edges. The system traces exact connections, giving the agent an auditable decision trace. An engineer can follow the exact mathematical path taken to block a transaction. By combining these graph algorithms with vector embeddings, a process known as hybrid search, we prevent the agent from making catastrophic logical leaps in production. The third and final component of the agentic stack is the behavior runtime. Coupling the probabilistic outputs of a language model directly to physical hardware is an architectural hazard. You cannot let models execute code without strict boundaries. This system architecture map illustrates the first principle of orchestration. The model dictates intent, but a deterministic gating mechanism must dictate the actual action. The model requests a tool, and the runtime decides if and how to deploy it. The second principle is serialization and interruption discipline. In a live environment, an agent receives asynchronous responses from external tools, APIs, and background processes all at once. If these streams aren't managed and organized into a single queue, the agent's coherence collapses entirely. The runtime must also enforce aggressive cancellation protocols. If a user interrupts a process or environmental states change mid-task, the runtime has to immediately clear the queue and reset the agent's motion state. When developers ignore this layer, infrastructure failures don't trigger standard error codes. Instead, they manifest to the end user as erratic hallucinations or bizarre personality flaws in the agent. The deterministic behavior runtime is the critical safety boundary. It keeps a probabilistic model securely grounded in operational reality. Stabilizing Software 3.5 requires all three of these engineering disciplines. This 3D architectural diagram shows the complete stack, building vertically. We see optimized disaggregated hardware at the base, the context graph acting as memory in the middle, and the behavior runtime managing execution at the top. These three specific layers exist entirely to compensate for the inherent speed, memory, and execution weaknesses of large language models. This architecture forces a complete reassessment of software development. The primary user of a B2B application is no longer a human clicking through a graphical dashboard. Products must now be explicitly optimized for agentic consumption. This means prioritizing headless APIs, structural data clarity, and programmatic interfaces over visual design and traditional user workflows. As frontier models continue to commoditize, having access to an LLM is no longer a competitive advantage. The true enterprise value will be captured by the teams who master the engineering discipline required to architect inference, memory, and runtime.